Hello and welcome to lecture 2. So, at the end of the first lecture we discussed the concept of limit. We motivated with the discussion of tangents and velocities, and now we're going to start to get to know this concept a bit better. So we'll start with the following example. So consider this. Let's try and understand this limit as t goes to 0 of the square root of t squared plus 9 minus 3 over t squared. Okay, so later we'll learn how to understand these things precisely, but for the time being let's just do this kind of numerical table that we've been doing previously. So the values of t over here, and this is our function, t squared plus 9 minus 3 over t squared, and let's just put in some values and see what we get. So let's do plus or minus 0.1, and this is 0.166620. Let's do plus and minus 0.05, and then this is 0.166655, and let's do plus or minus 0.01, and this is 16666, and then let's do plus or minus 0.0000001. Can't squeeze the 1 in here. And that turns out to be just 0.0000. Okay, so we're trying to understand the limit as t goes to 0 of this function. So in principle, the smaller value of t we get, the closer to the answer we should get. So up here, it's looking pretty good. It looks like the answer should be 1 over 6, right? But then as we put an even smaller value of t in, the answer goes from 1 over 6 to looking like it's 0. So what is going on? Do we have the limit of this thing is 0? Or is it something else? Is it 1 over 6? Well, again, a priori you might think the smaller values of t that you plug in, the closer it's going to be to the limit, because that's what the limit means. So you might think, okay, 0 is the actual answer. But that's not the case. That's just an error. And the reason is because if we just look at this part, and if we take t to be some incredibly small number, then the very best that your computer or calculator can do is simply store a certain number of digits of whatever this is, right? So maybe we can store the first, whatever, say 10 digits. And what this will actually be for very small t will be 3.00000, a bunch of zeros, and then some non-trivial stuff. Yeah? But it won't be able to store all that. So it'll just store what it thinks is the best approximation, which is the number 3 itself, right? So if we have this as our t, then t squared plus 9 square rooted is definitely bigger than 3, so this will be a positive number, right? However, the computer will just take it to be 0, because that's the best it can do. And we're dividing it by a very small number, so we have a number which is 0 on top, dividing by a very small number, we're going to get 0, which is why this 0 comes out here, right? But 0 is not the answer. In fact, the limit is 1 over 6. And this is a kind of useful illustrative example because we have the situation of growing up in a time of computers where these calculations almost feel like they're for free. It feels like we don't have to work particularly hard to find stuff out. We can just use some software, run some code, and get answers instead of having to think too much. In fact, computers have been around a while. There are many software packages, and in fact, most of you who will go off to be engineers will very rarely be doing calculations by hand. You'll only be doing that if it's some very simple thing that you don't want to bother to use any software for. But even that is even rare and rare because software is so easy to use. However, knowing what the software does is going to be a crucial thing, because if you have this blind faith in the answer that comes out of your computer, then you might really actually believe that your answer is 0 and not actually 1/6. And there's a big jump between 1/6 and 0. If this was some calculation that determined the crucial part of an aeroplane, then that difference could mean the aeroplane falling out the sky as opposed to flying safely, right? So this is one of the reasons why you are learning maths. It's because you can't just assume that you're going to get the truth out of a machine. The machine is just going to do the best it can do, but it's not a smart thing. It's just going to follow an algorithm. And the fact that it gives you an answer doesn't by any means that it's the right answer. So so I like this example to kind of clarify why we have to think so carefully about these things and learn them so well. If you do, on the other hand, have a good understanding of what is going on here, then you can interpret this as just a nonsensical answer. Right? All right, so that is first example. Let's talk about another function. This is the Heaviside function. And it looks like, well, let me first just give the definition. H of x is equal to 0 if x is less than 0, it's 1 if x is greater than or equal to 1. And what does it look like? So something that I'll be emphasizing is that you see something written in the language of maths and you're able to picture it in your head. And in the case of rather simple things like this, I'm hoping that that is something you're close to being able to do already. But let's just draw the graph. So we have, it's taking the value 1 for every x, wrote it wrong. Greater than 0. So it's taking the value 1 for every x greater than or equal to 0, right? And it's taking the value 0 for every x less than or equal to 0. It looks like this. Okay? If you can't easily picture this, if you can't easily just visualize it without drawing anything, then all you need to do is just draw all these things that you see. Every time you see some expression, some function, draw it. And just get in the habit of doing that, and pretty quickly your brain will take over and you'll just be able to read this and see it in your head without drawing it. That's this mental muscle of visualizing that you need to work on as quickly as possible. That's the tool that is going to benefit you the most going forward with respect to calculus and with respect to, in fact, all the mathematics you're going to learn. All right, so this is the Heaviside function. This is what it looks like, and our question is, does the limit as x go to 0, h of x, exist? And the answer, I hope you guys can see, is no. Let me try and get a different color. So if the limit existed, that would mean there'll be some number L, for example this number, where we could guarantee that the function was arbitrarily close to L, which means it's inside some tiny, thin neighborhood of L for every x very close to 0, but not equal to 0, right? And that's definitely not true, because if we took L to be just 1 here, then for all the x which are just a little bit to the left of 0, so less than 0, the values of h are 0 here, which is nowhere near 1, right? Conversely, if we tried to take L to be 0, then if we took x to be bigger than 0, the values of h is 1, which is nowhere near 0, so we can't trap all the values of h to be close to some particular limit. Let's draw the picture which represents limits again. So this is some graph. If this is A, and this is L, then we are able to force the function to be inside some thin strip around L by restricting the values of x to be very close to but not equal to A. And that's a key point we're going to bring up later. We don't care about the actual values of x at A. That's not inside the definition of limit. It just isn't noticed by the definition of limit. That's not important. Okay, so back to this. Does this limit exist? The answer is no. But you can say, well, it looks like it's got quite a bit of regularity or some kind of limiting type behavior. The real problem is that we're going from both directions. What if we just go from one direction? And sure enough, yeah, if we just go from one direction, then there is a limit. If we just went from the right-hand side, then we can guarantee the function gets closer and closer to the value 1. Yeah, as you can see from this picture. Conversely, if we just go from the left-hand side, we can guarantee the function gets closer and closer to the value 0. And this motivates this concept of one-sided limits. So one-sided limits. So we write this, the limit as x goes to A plus f of x equals L. So what this means is we can guarantee the function f gets arbitrarily close to L, as close to L as we like, so long as we're allowed to restrict the values of x to be incredibly close to the number A, but to the right-hand side of A. So this plus means numbers bigger than A to the right-hand side of A. So if I write this down in words, it's going to be completely cumbersome, but let me just do it. So it means we can force f to be as close to L as we like by restricting x to be very close to A, but greater and not equal to okay. So in words, it is quite a mess, right? But the picture is pretty easy. So in this picture, we just change it around a little bit. We could have our function, which does something like this, okay? And in this case, we can guarantee that the graph of the function is within this tiny, tiny neighborhood of the thin strip around L, so long as we restrict the values of x to be close to A, but to the right of A, and we have the right to make that little interval where it's true, where that holds as small as we like. No? Cool. So that is a one-sided limit, and this Heaviside function certainly has a wide-sided limit, so let's write that. So the limit as h goes to 0 from the right-hand side, h of x is equal to 1. Right? And the limit as h goes to the left-hand side, so we have an analogous definition for left-hand sided limits. When you approach from the left, is equal to 0. So it's exactly the same, except this time we're insisting that x is very close to A, but less than A. Okay? The left-sided limit is 0. So those are one-sided limits, and it's not hard to see that a function will have its limit exists at A if both the left and the right-hand side agree. So again, if the left-hand side limit and the right-hand side limit agree and they're equal, then the thing will actually have its limit. All right, let me erase the board, and we'll do an example. Okay, let's consider the following example. So I'm going to draw the graph of some function g, and we're going to have this 1, 2, 3, 4, 5, and this is only 1, 2, 3, and here. Okay, this is G. All right, so let's try and identify all the limits that we can see from this. So what we can see straight away is that if we look at 2, certainly there is no limit as x approaches 2, but there is a left and right hand side limit. So as we approach 2 from the left hand side, we're going to get closer and closer to the value 3. So we have the limit as x approaches 2 from the left hand side, g of x is equal to 3. If we approach 2 from the right hand side, then the limit is equal to 1. The limit as x approaches 2, the right hand side, g of x is equal to 1. And what about 5? Now this can trick some people. So the value of the function g at 5 is 1, right? But the definition of limit doesn't care about the actual value of the function at that point. It's not included in the definition, right? It just cares about what happens as you get closer and closer to 5, but not equal to 5. And as we get closer and closer to 5, but not equal to 5, then we get closer and closer to 2. So we actually have that the limit as x approaches 5, g of x is equal to 2, right? And this limit exists, it's perfectly good, even though g of 5 is not equal to 2, it's actually equal to 1. There's no problem here. And this is a classic kind of question that you can see in multiple choice, trying to see how well you've absorbed the definition of limit, because it's very natural to think that this limit doesn't exist or that the limit's equal to 1, but that's not the case. We were precise at what we said about the definition of limit, and it is indeed 2. We are all good with that. All right, cool. Let's consider this next example. This is a cool example. So let's take this function. So let f of x be equal to sine of pi over x. Okay? And our question is, does the limit as x goes to 0, f of x, exist? All right, so let's think about this a little bit. So let's just start by putting in some particular values of x. So suppose x is equal to 1 over n, where n is an integer. What happens? Then we're going to have f of 1 over n is equal to sine of n times pi, which you guys all know is 0 for every n, right? Cool. So if we try and understand what this thing looks like, we have a bunch of points, 1 over n, where the function is 0, and we might think, okay, that looks like it's telling us that the limit is 0. But let's check out some more things. What if we take, change color, take x to be 1 over 2n plus 1 over 2. Let's see what happens then. So f of 1 over 2n plus 1 over 2. What are we going to get? We're going to get sine of pi times 2n plus 1 over 2. which is sine of 2 pi n plus pi over 2. And you know, of course, that sine's periodic, so there's 2 pi n means that this thing is just equal to, let's put it over here, just a sine of pi over 2, and you know that that is just equal to 1. Right? So now we have another sequence of points that are tending to 0, where the value of the function is actually 1. Right? There's a bit too spaced to close together, but you see what I'm trying to do. Yeah? So, straight away from that, we know that we don't have any kind of limits. We don't have a limit at 0, or a left-hand-sided limit, or a right-hand-sided limit. Because if we approach just from the right-hand side, we're getting values very close to 0, or actually equal to 0, and values actually equal to 1. We can't trap it close to any particular value. And the same for the left, right? So, therefore, there is no kind of limits of any kind. So, no limits at all. So it looks like a kind of unusual function, even though it's quite simple to write down. Symbolically, it's not looking particularly bad. Let's try and understand what it actually does. So, in class, I ask people to sketch this. They typically have a lot of difficulty. And it's because it's a composed function. So, let's try and understand it. This is meant to be a different color, but looks exactly the same. So when we have a composed function, we can think of this as two machines, right? So you take your number x, you act on it with the first machine, which is just x goes to pi over x, and then the second machine is to act on it with sine, right? So you can think about this x to pi over x as shifting u to a different position on the x-axis, and then you're acting on it with this function sine. Yeah? So this is a little metaphor. So imagine that you are walking towards 0 at a constant speed, and then you get acted on by the function x goes to pi over x, right? That's going to send you shooting off towards infinity. The closer you get to 0, the faster you'll be heading off towards infinity, right? So then you will be then transported towards infinity at quite some rate, yeah? And then after having done that, you're going to be acted on by sine. And imagine being acted on by sine is like experiencing a sound where if you are above part of the graph where sine is positive, you hear a high sound, and if you're above part of the graph where it's negative, you hear a low sound. So the graph of sine is like this, and you're being transported along the x-axis faster and faster and faster. So what sound will you hear? Well, you'll hear it go high sound, low sound, so beep, 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 beep. But then as you're going faster and faster along this x-axis, the beeps will go faster, so beep, 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 like this, right? So if we just draw directly a graph of what you experience as you walk in steady pace towards 0, it'll be something like this, right? You'll be hearing these sounds that oscillate up and down, up and down, up and down with the same amplitude but greater and greater frequency, right? In fact, it's going to oscillate infinitely many times before we get to 0. And on the other side too. Oh, damn it. I could do this a better picture, but you can see what I'm trying to do here. It's a really cool exercise just to type this into some software and see what it produces. So that makes sense according to what we see, right? Because then there are indeed lots of points where it's going to take the value 0 as we go towards 0, and also lots of points where it takes the value 1 as we go towards 0. Yeah? In fact, for any tiny neighborhood around 0, it's going to take every single value between -1 and 1. Yeah? This is indeed a very wild function. Yeah? Looks innocent symbolically, but its actual behavior is very dramatic. And this is another example of the power and the utility of visualizing things, right? If you've got into this habit of seeing something written in the language of math and then picturing it in your mind, then the answer to this question, does this have a limit as x goes to 0, will be instantly clear to you. It's absolutely not the case it has any kind of limit, right? And this might be rather kind of a hard example, and probably most of you can't instantly visualize that in your minds. But if you have some ability to do that, you'll notice that this is not coming clear to you. So this isn't some trivial function. This is probably something a little bit subtle, and at least that will tell you, okay, I've got to think harder about this, got to examine this more closely, and then you'll start to see what's happening. Yeah? Yeah? That's what you should start to try and do. Yeah? Visualize this, and even if you can't visualize it, that information will give you something. As you get in the habit of visualizing, drawing pictures to represent all the math you see, you'll find that your brain picks it up remarkably fast. You will not have to actually sketch, you'll just see it. Okay, let's keep going. Okay, let's consider the following function. And our question is, does limit as x goes to 0, f of x exist? Once again, we're going to visualize this function. What do we see? We see it looks like this. It's always positive and it blows up around 0. Yeah? So, does this exist? Well, no. The only way the limit could exist is if there was some number L where we could trap the value of the function to be arbitrarily close to L, so to strip around L as we restrict the values incredibly close to 0 but not equal to 0. And that's definitely not the case, right? This thing's blowing up to infinity. Yeah? However, you might think, okay, well, it's got some very regular behavior as we go towards 0. Is there not some sense in which I can write or say something? And indeed, that's true. So, it is however the case that the limit as x approaches 0 of this function is equal to infinity, which we're going to write this way. The limit as x goes to 0, f of x is equal to infinity. Important point. We do not say that the limit exists, because when we say the limit exists, it exists as a number. Infinity is not a number. Such an important point that I threw my pen in the air. Okay, let's write it down. So, okay. So even though we write this, we write something in the language of math, which is the limit is equal to something, it nevertheless, it's a linguistic convention, it's nothing deep. We say that the limit does not exist, because when we say the limit exists, we mean it exists as a number. Okay? And again, this is something else that can be tested on a multiple choice. So the limit does not exist. Let me change cans just to emphasize it. Because the limit does not exist as a number. Okay? But in general, we can give some meaning to this. So when we write the limit as x goes to a, let's give a different letter, g of x equals infinity, what does this mean? It means that we can guarantee that g is bigger than any number at all that we choose, so long as we restrict the values of x to be sufficiently close to a, not equal to a. So again, I write this in words, it's going to be very cumbersome, but then we'll draw the picture. So it means okay, as I said, lots of words, lots of mess here. The picture, however, is very clear, very nice. So if this is a, then we mean that the limit of g as x approaches a equals infinity means that whatever big number you choose, however big it is, you can guarantee that your function is going to be bigger than this big number for all x sufficiently close to a, not equal to a, where you have the right to choose this tiny interval, right? So you get given some big number and you say, okay, I can guarantee you that g is going to be bigger than that big number if I get to choose the interval around a, yeah? And that's true for every single big number. And you can see that that's definitely the case for this function 1 over x squared. We can guarantee it is bigger than any big number that you like, right? Pick your favorite biggest big number, right? You can get this function bigger than that number so long as you restrict your interval to be sufficiently small around 0, not equal to 0. Yeah? So the picture is this. So this is the function g. We have the close up like this. Right? You can do some other stuff at other places, but this is what it does here at a. Okay, so it's very similar to the other definition, except how would we get close to infinity? We get close to infinity by being bigger than any big number given, right? All right, so we can also define left and right-sided limits. So I'll simply define the limit as x goes to a plus, g of x equals infinity or a minus. Or we can have that the limits, either left or right-sided limits, are negative infinity. Or the limit as x goes to infinity, g of x equals negative infinity. And then the definition is analogous. So take your most negative number, minus 1,000,000 trillion. You can guarantee, I've written nonsense here. You can guarantee that g is going to be less than 1,000,000 trillion so long as you're in a sufficiently small neighborhood around a, not equal to a. And that's true for any negative number you choose. That's what it means to have the limit as x approaches a to be negative infinity. In the picture, of course, something like this. So here is a, g can do anything else around here, but as we get towards a, we can guarantee that we are more negative than any negative number you can choose, right? And we can also define left and right-sided limits. So, and similarly, the left side limits is minus infinity, and the right side limit okay, so those are limits that do not exist, but we can still write them, and we say the limit is infinity. All right, let me erase the board and give you some more definitions. Okay, so if we have that the limit as x approaches a, f of x is either plus or minus infinity, or the limit as x approaches a from the left-hand side, f of x is either plus or minus infinity, or the limit as x approaches a from the right-hand side, f of x is plus or minus infinity, then we say that f has got a vertical asymptote at a. Okay, and of course it comes with a picture. So graph. Here we are at A, and if we had the limit was infinity, it would be going up like this. If we have the limit as negative infinity going down like this, so we have any one of these behaviors. So for example, this is the limit as x approaches A from the right-hand side. A plus is infinity, and then it can just be anything else like this, or it can have the limit of the left-hand side being infinity and the limit on the right-hand side being negative infinity, or any kind of combination of things like this. So in this case, the limit as x approaches a from the left-hand side, f of x equals infinity. So infinity like this. Okay. So you have some vertical line where the graph of the function is basically crawling up or crawling down this vertical line. Yeah? That is a vertical asymptote. Cool. All right, so let's consider an example. So, example. What about the limit? Let me write it in words. So let f of x be 3x over x minus 3. So what limits do we have at 3? Okay, well, at 3, as x approaches 3, then the thing on the top is approaching 9, the thing on the bottom is approaching 0, either from the left or the right, so either from small positive numbers or small negative numbers. So this thing has to be tending either towards positive or negative infinity, and we'll figure out which in a second. But it's definitely either positive or negative infinity, therefore this limit won't exist as a number. So we can write the limit will be maybe infinity, negative infinity, but what limits does it have at 3? It has no limits. It doesn't have any limits that exist at infinity. So Oh, sorry, it doesn't have any limits that exist at 3. So no limits that exist as a number. So we say it doesn't have any limits at 3. Okay, but if we look, let's say we go from the left-hand side. And at this point, I want to draw a picture. So on the top, we know as we get towards 3, it is close to 9, right? And on the bottom, it depends which side we go from. So if we go from numbers that are less than 3, yeah? So it's like 2.99 or whatever, then a number less than 3 minus 3 is going to be a very small negative number. So on the top it's like 9, on the bottom it's a very small negative number, therefore it has to be going down like this. Yeah? And as we approach from the right-hand side, from numbers that are a little bit bigger than 3, but getting close towards 3, then it's like 3.001 minus 3, so it's a very small positive number on the bottom, and on the top it's still like 9. So it's going to blow up towards infinity like this. So it'll have a vertical asymptote. Right? So the limit that's going from the left-hand side will be minus infinity, and the limit as x approaches 3 from the right-hand side will be equal to infinity. Now, either one of these things is enough for us to conclude that this thing's got a vertical asymptote at 3. But we actually have both. So f has a v, so I'm going to write v asymptote for vertical asymptote from now on. Add 3. All right, let me see if I can squeeze the rest in on the bottom of this board. Let's consider this function. So let f of x be tan of x, which is sine of x over cosine of x. Okay, sine and cosine are these basic elementary functions whose graph hopefully you are quite comfortable with. And if you're not, then just draw them, sketch them, work them out until you are happy with them. So the graphs in here. So what does the sine look like? It looks like this, goes up like this, crosses at pi, goes back at 2 pi, like this, right? This is sine, this is pi. What does cosine look like? Cosine looks like this. It's 1, crosses pi over 2. Here we are at pi, 3 pi over 2. This is pi over 2. And it's symmetrical like this. This is minus pi over 2, and this is minus pi. And this here is minus 2 pi. And this is minus 3 pi over 2. Okay? This is cosine. So, when are we going to have vertical asymptotes? Well, it's only going to happen, well, it can only happen when sine is 0. Right? It might not, as you'll later find out, it doesn't always happen when the bottom is 0, because the top could be 0 as well, and it could be tending towards 0 at the same rate, or the top could be tending towards 0 faster. So the fact that something's 0 on the bottom doesn't necessarily guarantee you that you have a vertical asymptote. But in this case, we are fine, because whenever sine is 0, we are here, right? And then cosine is not equal to 0. Yeah? So let's try and figure out what happens. So this here is pi over 2. This is minus pi over 2. Let's see what the vertical asymptotes of tangent are as we approach pi over 2 from the left-hand side. So the limit as x goes to pi over 2, negative from the left-hand side, what's going to happen? So as you approach pi over 2 from the left-hand side, sine is tending towards 1, right? But cosine is tending towards 0, but it's going to be tending towards 0 from the positive numbers. So on the top we'll have something like 1, on the bottom we'll have a very small positive number, which gets smaller and smaller and smaller, right? So, and this thing will have to be infinity. Yeah? What happens if, let's change color, this one might be a bit too dark. What about the limit as x approaches pi over 2 from the right-hand side? If we approach from the right-hand side, okay, from the right-hand side again, sine is closer and closer to 1, but now it's from the right-hand side, cosine is approaching 0 from the negative numbers, right? You see it right here. Yeah? So on the top we have something close to 1, on the bottom we have a very small negative number. So this thing has to be negative infinity. Yeah? Let's go here and figure out what happens at minus pi over 2. So the limit as x approaches minus pi over 2 from the left-hand side. Now, at minus pi over 2, sine is minus 1. Yeah? So as we approach minus pi over 2 from the left-hand side, we're getting closer and closer to minus 1. Yeah? But as we approach minus pi over 2 from the left-hand side, from numbers which are less than pi over 2, we also have a negative number here, right? So on the top we'll have negative 1, on the bottom we'll have a very small negative number, right? And that very small negative number gets closer and closer to 0. But we're actually going to have a negative number over a negative number, so it's going to be a positive number. So this thing will be infinity. And let's do this guy. The limit as x goes to minus pi over 2 from the right-hand side, tan of x. So once again, as we approach minus pi over 2 from the right-hand side, with respect, when we're looking at the graph of sine, we see it's tending towards minus 1. As we approach minus pi over 2 from the right-hand side, expect the cosine is tending towards 0 from the positive numbers. So we have minus 1 over a very small positive number. So this will be negative infinity. Right? So let's try and draw the graph a bit on this bit of space we have here. So this here is pi over 2, and this is minus pi over 2. When we are close to 0, then as we're later going to, the graph of sine looks like this. Graph of cosine is 1, so it's going to kind of just look like sine itself, right? And as we go towards pi over 2 from the left-hand side, from numbers less than pi over 2, we are tending up towards infinity, right? So it's going to blow up like this, have a vertical asymptote like this, right? And as we approach pi over 2 from the right-hand side, numbers that are bigger than pi over 2, then we have this kind of vertical asymptote like this. Okay? And as we approach pi over 2 from numbers which are, as we approach minus pi over 2 from numbers which are bigger than minus pi over 2, it's this guy, with negative infinity, so it looks like this. And as we approach minus pi over 2 from the negative numbers, from the left-hand side of minus pi over 2, positive infinity, so looks like this. Yeah? And I'm sure most of you have seen the graph of tan before, but here we've worked it out using what we now know about understanding vertical asymptotes and understanding left and right-hand side limits. Okay, so that's it for today. See you all on Friday. Oh, see the Friday group.